let's look at this similar triangle problem. So one of the things that you're going to have to get really good at in these questions is reading the question, interpreting what's all there, and then drawing some sort of diagram or picture to represent what's happening. So here we've got a spotlight on the ground shining on a wall 10 meters away. A man is walking from the spotlight towards the wall, and we have his speed, and we want to find out how fast his shadow is decreasing when he's 3 meters from the wall. So you have to decide where you're going to put your wall. Some people will make a right triangle this way, some people put the wall in the right triangle in the other way. It really doesn't matter. So I'm going to put my spotlight right here, color in some bright shining light so that we can really imagine that as a spotlight. Now it's shining on the wall, so what that does is the light makes a right angled triangle. Now we have a person who's walking away from the spotlight towards the wall, and we want to find out how fast the shadow on the wall is decreasing. So I'm going to call his shadow on the wall y. We know that y is a function of time, and we're trying to find dy dt. So this is what we're trying to find. We know another speed. We know that he's walking towards the wall at 1.2 meters per second. And we know that this spotlight, to begin with, is 10 meters away from the wall. So at this moment you have a decision to make. We need to put x somewhere. We can decide to put x here to represent the distance that he's away from the wall, or we can decide to put x here to represent the distance that he's away from the spotlight. Both of them will give us the right answer in the end, but they will change how we set up our question. Okay? Now, probably if I was looking at this question trying to make that decision of what I wanted to do, I see in the end it says, how fast is his shadow decreasing when he is 3 meters from the wall? So they're talking about this distance being 3 meters. So I might put x there, just so that later on when I need to plug in x, I can plug in x equals 3 at that point. If I put x there, that means this will be 10 minus x, because the whole length is 10. So now we know that x is also going to be a function of time. And this is why it was really important for us to decide where x is going to be. Because what's happening to x? Is it getting bigger or is it getting smaller when he's walking at this speed? It's getting smaller. So when we have our dx dt, we have to write that as a negative 1.2 meters per second. Can you see if you would have put the x at the other spot, then the x would be getting bigger. And so then you would write it as a positive 1.2 meters per second. So the setup of this really gets you thinking and really gets you trying to set things up and figure out what's going on. Now that we've got dy dt and dx dt, we need to come up with an equation that relates these. So in a similar triangle problem like this one, can you see that the triangle that's made with the 10 minus x and the man is a similar triangle to the entire triangle that's there? The angles will all be the same because they'll share the angle at the spotlight. They both have 90-degree angles, and so the other angle would be the same as well. So if they're similar triangles, ratios are the same. The ratios that we have here, while we know the man is 2 meters tall, we have the opposite and adjacent sides of both of those triangles. So setting up a ratio, we know that in the big triangle, y over 10, which is the opposite side over the adjacent side, if we're talking about the spotlight as our angle, has to equal 2 over 10 minus x. Multiplying this out, we'll get 20 minus xy, 10y minus xy is going to equal 20. Well, I multiplied both sides by 10 minus x. And distributed that with the y. And I multiplied both sides by 10 just to get rid of my fractions. Now I can find the derivative with respect to time of this expression. Can you see that you're going to have some implicit differentiation here? First of all, the derivative of 10y is just going to be 10 dy dt minus the derivative of xy is going to have a product rule. Take the derivative of x, keep the other one the same, plus keep the other one the same, and the derivative of y. Then the derivative of 20 will just be 0. We are trying to find dy dt. That's what we want to find. We can put dy dt all on one side. We're going to have 10 dy dt, subtract x dy dt. If I move this dx dt y to the other side, we've got the following. We can now factor out our dy dt and get the following. Now we want to find out how fast the shadow is decreasing when x is 3. So now when we plug in x is 3, dx dt we knew was negative 1.2, and we need to find out what is y when x is 3. So another thing that we have yet to find out is what's the value of y when x is 3. So if we set up our triangle again and just have a look at this, we know that this is 10. We know that the height of the man is 2, and this part here is 3, making this part 7. How high is it at that moment? How high is the shadow? Again, we can use our similar triangles. We know that y over 10 is similar to 2 over 7. So at this moment, the height is 20 over 7. Dividing both sides by 7 and multiplying these things out, 20 times that will be negative 24 over 49 meters per second. 20 times 1.2, yes, 24. So the shadow is decreasing at negative 24 over 49, almost a half a meter per second at that time. So again, here we had to set up our similar triangles, one to get our equation, and also to figure out values within that equation. So we noticed here that we didn't have a value for y, but when you're finding out a specific point when x was equal to 3, we could draw that picture out. When x was equal to 3, y is equal to 20 over 7. Yes?
Just near the top, why do you have y over 10 is equal to 2 over 10 minus x?
Right here?
Yeah, how'd you get that?
Again, that's from our similar triangle. So if I draw it out here, basically this is my big triangle. This is my y and my 10 in that big triangle. Then in my smaller triangle here, which is similar, this is 2 and this is 10 minus x. So if triangles are similar, then their ratios of their sides will be similar. Another way to look at it is if we make this angle theta, tan of theta is opposite over adjacent. And if we use the red triangle, our opposite over adjacent is this. If we use our blue triangle, our opposite over adjacent is that. And since they both equal tan of theta, they both have to be equal themselves. Sometimes what people do as far as ratios of similar triangles is you may be more familiar with saying, well, I'll compare the similar sides. So here's 2 and y, those are similar sides. And here's 10 minus x and 10, and those are similar sides. So the ratio of y divided by 2 has to be equal to the ratio of 10 divided by 10 minus x. Can you see that's not the same setup as we had before, but when you multiply things out, you're going to get exactly the same thing. So it depends on how you're visualizing, how you're setting up your ratios. The time that I set it up here, I was thinking of the tangent ratios and having those ratios be the same. If you want to say, well, I know these triangles are similar, so this times something has to be the same as this times something for the sides, and you could set up your ratio this way as well. That would also work. Yes?
Why did you have to apply the 10 minus x to both sides? Didn't you just have...
Yeah, I could have done the derivative of each side separately as well. So what he's saying is, could you have kept them as fractions and then found the derivative from there? And the answer to that is yes. It would make the derivative on the left side easier because you would just get 1/10 dy dt. On the right side, you would have a chain rule, and but it would work out to the exact same numbers.